Cyclic behavior of steel tube confined circular RC columns under high high axial load. The circular behavior of steel tube confined circular reinforced concrete RC columns under high axial load refers to the response of these columns when subjected to cyclic loading conditions which might occur in seismic events, wind loads, and other dynamic conditions. The behavior of these columns is crucial for understanding their performance and durability in seismic prone areas like s- steel tube confinement. The steel tube around the RC column provides the confinement which enhances the strength and ductility of the concrete core. When cyclic loading is applied, the steel tube prevents lateral expansion of the concrete and helps to maintain its integrity and reducing the potential for brittle failure. Next, high axial loads and confinement. The relationship between high axial loads and confinement in steel tube confined reinforced concrete RC columns is fundamental to understanding the performance of these columns, especially under dynamic or seismic loading conditions. The concept of confinement refers to the use of external materials like tubes, materials like tubes, steel to enhance the strength, ductility, and energy dissipation capacity of the concrete core. High axial loads in constrained columns. High axial loads in structural elements such as RC columns can significantly influence their behavior under loading conditions. Axial load refers to the vertical compressive force acting on the column, and it is often a primary factor in determining the capacity of concrete structures. When axial loads are high, they push the concrete core into compression, and under confinement, the response of the material can change. Concrete behavior under high axial loads without confinement. High axial loads, when applied to an arched column without any form of confinement, confinement can lead to premature failure of the concrete due to crushing, especially if the concrete is unable to bear the load beyond its compressive strength. And concrete exhibits limited ductility and compression under these conditions. With confinement steel tube, the application of confinement through a steel tube prevents the concrete from laterally expanding, which enhances its compressive strength and ductility. Ductility. The confinement improves the concrete's ability to withstand higher axial loads without falling and increasing the column's load carrying capacity. Experimental setups, materials and methods. In the context of investigating the cyclic behavior of steel tube confined circular reinforced concrete RC columns under high axial loads, the materials and methods section is crucial for describing the experimental setups. Uh, Materials, concrete in concrete mixed design. The concrete used for the RC column specimens should be designed with a specific proportion based on the desired strength. Typically, a high strength concrete mixed with a compressive strength ranging from 30 MPa to 80 MPa may be used depending on the actual load levels and its material properties. Compressive strength: the compressive strength of the concrete should be determined using standard cylinder testing ASTM C39. Next, steel tube confinement material: the steel tube used for confinement should typically be made of carbon steel with an appropriate yield strength, commonly ranging from 250 MPa to 500 MPa. Geometry: the steel tube is generally circular with a specific thickness to provide adv- ad- adequate confinement. Uh, the dimensions should be chosen on the desired level of confinement and axial loads. The typical steel tube thickness could range from 3 millimeters to 10 millimeters. Yield strength and modulus of elasticity is steel tubes. Yield strength and modulus of elasticity should be tested according to relevant standards such as ASTM A500 for structural tubing and reinforcement, specimen preparation, and etc. Next, varying axial load ratios. The axial load ratio, often denoted as P by P underscore U, is the ratio of the applied axial load P to the ultimate axial load capacity PU of the column. This ratio reflects the level of axial load relative to the maximum load to the column can resist in compression. In compression, axial load ratio is equals to P by Pu. P is applied axial load on the column in kilonewtons or newtons. Pu, ultimate axial load capacity of the column in kilonewtons or newtons. An axial load ratio closer to 1 indicates that the column is under a high axial load close to its ultimate capacity, whereas an axial load ratio significantly less than 1 indicates that the column is under low axial load relative to its maximum capacity. Importance of varying axial load ratios. Varying axial load ratios are essential for, for studying the performance of the steel tube confined RC columns, particularly under cyclic loading. The axial load ratio directly influences the column's strength, ductility, and stability under different loading conditions. The effects of axial load on the cyclic behavior of confined RC columns under seismic conditions need to be understand to design more resilient, resilient and durable structures. Next, buckling and crushing. Buckling is a failure mode that occurs when a column experiences excessive axial load or lateral displacement, causing it to deform lateral, lat, laterally rather than compressing vertically. This mode of failure is typically associated with the steel tube or the reinforcement of the RC column, but can also involve the interaction between the concrete core and the steel confinement. The types of buckling: steel tube buckling. The first one, steel tube buckling. The steel tube surrounding the Concrete core is meant to provide lateral confinement, preventing the concrete from expanding laterally under compressive loads. However, if the axial load exceeds a certain threshold, the steel tube itself may buckle. Local buckling of the tubes occurs when the tube walls deform inward due to compressive forces resulting in a loss of lateral confinement. A longitudinal reinforcement buckling. Inside the concrete core can buckle due to the compressive axial load. This is especially common in slender columns that are more susceptible to buckling failure and combined buckling and confinement. The presence of the steel tube sorry confinement can delay buckling by the restricting the lateral displacement of the concrete. However, at high axial loads, the confinement may, may be unable to prevent buckling of the steel tube and the reinforcement, leading to a combined failure of the tube and core. Crushing. Crushing refers to the failure of the concrete core under high compressive stress, where the concrete reaches its compressive strength limit and experiences irreversible deformation, usually in the form of spalling or complete fracturing. Crushing is a common failure mode in reinforced concrete columns under high axial loads, particularly when confinement is inadequate. The types of crushing. Concrete crushing in the core. Concrete crushing cores occurs when the compressive stress within the concrete core exceeds the material compressive strength, leading to its failure. This typically happens when the axial load ratio P by Pu is very high. The next, the second one, concrete spalling. Spalling is the shedding of small pieces or chunks of concrete from the column's surface due to excessive compressive stresses. Spalling is often observed in the outer layers of the concrete core and can compromise the column's overall strength, etc. Next one. Energy dissipation characteristics. Energy dissipation refers to the process of observing and converting the input energies, such as a form of an earthquake, into another form, typically through plastic deformation or hysteresis. In the context of columns, energy dissipation happens as the column deforms under applied loads, particularly in the inelastic region of the stress strain curve. This dissipation helps helps to prevent the column from failing abruptly by distributing the forces more gradually. For steel tube confined RC columns, energy dissipation typically occurs due to plastic deformations in the both concrete core and the steel tube. Hysteresis behavior exhibited under cyclic loading, frictional forces between concrete and the steel tube, etc. So, right. Calibration and validation. Calibration. An analytical model was calibrated using experimental data to ensure accurate representation of the column's behavior. Validation. Validation involved comparing simulation results with experimental observations, ensuring model reliability. Influence of steel tube thickness. Enhanced confinement. It refers to the process of improving the lateral support provided to the concrete core by the steel tube surrounding the columns. This additional confinement increases the compressive strength, ductility, and energy dissipation capacity of the column, especially under high axial loads or cyclic loadings, such as during seismic events. Confinement is a critical factor in improving the, the performance and safety of steel tube confined reinforcement concrete RC columns under both static and dynamic loading conditions. Conclusion. The study of steel tube confined RC columns under high axial loads and cyclic loading reveals the significant role of confinement in enhancing the column's strength, ductility, and energy dissipation capacity. The steel tube provides vital lateral support to the concrete core, preventing premature crushing and allowing the column to undergo larger plastic deformations without failure. Enhanced confinement improves the compressive strength of the concrete core, increases the load carrying capacity, and ensures the column can withstand seismic demands by dissipating energy efficiently through, ha- through, through higher static acidic behavior. Thank you.